just say the illustrations are simple. Projecting them is more difficult.
Good.
All right.
Which button goes forward? Which button goes backwards?
The down one goes forward. The top one goes up. And you've got a little bit pointer.
Okay, the bottom one goes
Go down. Yep.
And I have half an hour, right?
Yeah.
Okay.
Okay. I know we're all anxious to go see what's out at the coffee break, but Jasper Nice from, I think you said you were from Edmonton.
That's correct.
Almost local. Simple 3D illustrations in the tech ecosystem. And as I've seen in the past, while it may be simple in the tech, connecting the computer to the projector does land a few problems. So Jasper.
Thank you very much. Hello, everybody. Oh, I'm not going to use the microphone. Can everyone in the back hear me? Yeah. Awesome. Before I get started, I just want to say a few remarks. I want to say thank you for everyone who came. I want to say thank you for everyone who wasn't able to come but who is still part of our community. Thank you, Boris, and everyone else for hosting the YouTube chat. And if I know you through Tech Stack Exchange, hi. Should probably pull the remote. Yes, and I wouldn't be here presenting, at least, if it weren't for Barbara Beaton's suggestion. So thank you, Barbara, for suggesting this talk. We're going to talk about simple illustrations in the tech ecosystems, specifically 3D ones. We're going to start with, there are 3 sections. The first section has 3 subsections. Second section has 2 subsections. You can count. We're going to start with the overview. We're going to talk about the problem that I'm talking about. We're going to talk about why it's important. And we're also going to explore a bit about why I chose Lua LaTeX as my platform. Without being addressed. We are going to study something here called, this is going to sound scary, affine algebra. Ooh. We're going to motivate it, though. We're not going to introduce it out of nowhere. This diagram is made out of triangles. Triangles are very special. Triangles are a type of simplex. A simplex is a line segment. In the context of this talk, a simplex is a line segment or a triangle. The interesting and very fascinating thing about line segments and triangles is that they are equivalent to bases in linear algebra, whereas I like to call them affine bases when they are not when they have a point of origination that is not necessarily the origin. In linear algebra, the origin doesn't matter. In affine algebra, the origin of a vector definitely matters. And so the cool thing about that is that when we represent a triangle as a basis, we can do a bunch of affine algebraic reasoning with it that lets us do 3D stuff. We will explore this as we go. So I talked to you about something called the simplex basis correspondence. That is what I like to call it. Every triangle is a basis. Every line segment is a basis. When I take the illustration of intersecting planes, I represent the triangles as bases, and I use Gauss-Jordan on their bases to find the intersection subspace. We will get into that later. Triangles are bases, and bases span something called a subspace. A subspace, if a basis has 2 vectors sticking out of a common point of origin, the subspace through that basis is the plane that's spanned by those 2 vectors. If you have 1 vector out of that point, the span of that basis is a line through that point in the direction of the vector. I hope that is clear for you guys. I'm very used to this stuff. We will develop it intuitively, is my plan, without too much fancy jargon. My hope is to not overload you guys with jargon. I want to introduce everything in terms of stuff that you can visualize in your head infinity symbols. So that is the plan. This is a Klein model. You don't need to know the definition of a Klein model, but I'm sure most of us know what a Klein model looks like. Why is this issue important? Spatial illustrations are everywhere. The basic transformations, when we deal with affine algebra, there are two important parts of it. There are affine operations, such as addition, subtraction, dot product, cross product. These are fancy terms. Addition and subtraction are valuable for navigation of bases, of subspaces through bases, because when we do that, we take a linear combination, or an affine combination of the protruding vectors out of the point of origination in order to navigate the plane through, say, a triangle. There are also transformations in affine algebra which are different from the operations. A transformation is accomplished through matrix multiplication. In linear algebra, we have matrix multiplications. Some of you who have taken linear algebra or taught it will know what these are. Some of you also know what affine transformations are. Affine transformations are linear transformations that include translation. So there are linear transformations that include translation, because that is not included in linear algebra. And that lets us do a lot of cool stuff in 3D, as you can imagine, because linear algebra gives you rotations, and affine algebra gives you translations. What am I doing right now? I'm rotating, translating. So, as I've mentioned, I'm going to drill this point home many times throughout this talk. A simplex is a basis. When all of these triangles here, when I tessellated this domain, this parametric function, I took a rectangular domain and mapped it onto 3D. This function jumps up through the ceiling. How did I stop that? I put an invisible bounding box, bounding cube of triangles around it, and I partitioned them by these triangles. The way I did that is I used something called Gauss-Jordan on their bases. Because when you take Gauss-Jordan, it's so cool. It lets you identify the intersection set of two subspaces in linear algebra, but it also works in affine algebra and projective algebra. And what that let me do is I was able to identify the line segments which span the one-dimensional subspaces through both the triangles of the green diagram and the triangles of the invisible bounding cube. And then by extending those one-dimensional bases, I was able to identify the intersections with their parent triangles and partition those parent triangles by those intersection points. Afterwards, I was able to remove everything above this diagram that would have gone straight up into the ceiling using a Boolean filter. And we get this cool little image. You can see how it turns into a perfect grid when we look at it upright. The opacity of the plane is not that high, so you do not see it, the occlusion too well, but if you look closely here, it is actually more gray there, but probably not on this screen. I forget who suggested this diagram to me. I believe it was Barbara, but I might not be. I looked for the original citation and I could not find it. Parametric domains are often simplicity tessellated. Oftentimes there are other ways to do it. There are other ways to illustrate parametric objects. I really like simplices because, well, as I've described, the intersection of two simplices is a simplex, and it always reduces down to operations and simplices. It is very nice. So, this picture is wrong. Why is it wrong? We did not identify the correct intersection points of the line segments composing the gravity field and the intersections of them with the sphere. If we took the actual intersections, they would not be on the straight-up triangles that comprise the sphere. They would actually be 1 unit away from the sphere's center, which is not always true when you intersect a triangle which is on a tessellated sphere, especially when you do it according to the Cartesian product of domain sequence sampling, which is the way everyone does it these days, unless they do Dillon triangulation. Why did I choose Lua LaTeX as a platform? This is actually a really cool story. It goes back to a conversation I had with Max Chernoff in the chat. Some of you were there for that. hands down. So I learned TIX. Some of you who know me from Tech Stack Exchange will know that I've spent years posting about TIX on 2 accounts. I love illustrating. It is something that I just find so much joy in. This is not the animation in question. We will see that one later. This is a stereographic projection of a spinning sphere. I think it looks cool. I love stereographic projections. It's very similar to the diagram that took 16 hours to render 24 frames of. Yes. Maximilian, thanks to you, that same animation was well under 20 minutes in Lua. We will see that animation later. Oh, isn't that amazing? How does this work? I call it technical detail. Don't let that intimidate you. We're going to do another friendly introduction to affine algebra, because sometimes you need to repeat yourself to get a point across. The 3D affine vector is a list of 4 numbers. Most commonly, the last number is 1. In projective algebra, you can change that to do perspective transformations, but we're not dealing with that here. The cool thing about an affine vector is, unlike a linear vector, its origin matters. It really matters. If an affine vector is here, it spans a line through its basis here, not over here. That is very important for navigating subspaces, which is very important for doing things like partitioning and occlusion, which we will get into in small detail as we go along. The important operations are addition, scalar multiplication, the dot product, and cross product. Addition and scalar multiplication enable navigation. You add scalar multiples of affine vectors in a basis to navigate the subspace spanned by that basis, just like in linear algebra. So if you have 2 vectors pointing like this from a common point of origin, you can traverse the plane through them using just them. It reduces down to Gauss-Jordan, and it is something that I really enjoy, at least. The dot product and cross products are also very cool. The dot product gives us a means of reasoning about angles and projections, and the dot product gives us a means of reasoning about orthogonality. For example, with dot product, I can tell you how far in a specific direction normal to a vector relative to a vector something is. Without the dot product, that would be very difficult. With the dot product, it comes immediately. The cross product lets us generate orthogonal vectors, which point in perpendicular directions to one another. That is useful for developing something called an orthonormal basis, which is useful for a lot of things in algebra. An affine basis for a 3D line segment consists of 2 3D affine vectors. One of them is the origin. One of them is not the other end of the thing, but the direction vector that points to it. So if you had a line segment, the way to turn that into an affine vector would be to subtract the first point from the second point to turn the second point into a vector protruding from the first point to the second point, while keeping the first vector fixed. That turns it into a basis. They can also get turned back into a simplex, but you don't usually do that. An affine basis, and for a triangle consists of 3 affine vectors. One of them is the origin, and 2 of them protrude from the origin. You guys can see how poorly I tessellated down there. That's because I partitioned those triangles so you wouldn't see anything that was on this side of it. Yes, it does not look as good as the original, but it is better than the one that was there this morning. Yes, in this diagram, actually, we use inverse affine transformations to normally, depending on which perspective you take, they're both valid. You can decide to move the camera or move the objects relative to the camera. I like to move objects relative to the camera. So I take the transformation that moves the camera there, and I perform the opposite of it on everything else. It's called an inverse affine transformation, and it's usually how cameras are achieved in graphics. We use matrix multiplications to compose transformations. And the homogeneous coordinate, which is the number 1 at the end of the affine vector, is what lets us do translations. Translations are a phenomenal thing to add to linear algebra because useful for understanding reality. There are lots of nonlinear transformations that are useful. Translation and rotation are pretty fundamental to 3D graphics. And as I've mentioned multiple times, Gauss-Jordan elimination is used to determine the intersection sets of affine subspaces, which are themselves affine subspaces unless they don't exist. But if it does exist, it is an affine subspace. It reduces, it's beautiful. Simplices reducing to problems of simplices. You don't leave that class. It is something I very much like. Simplicial occlusion and partitioning. I promise I'll keep it basic. Occlusion ordering in the system, the way we do it is we project two simplices, in this case triangles. I'll treat it as triangles. A lot of people find that more intuitive, I would imagine. You project them onto the viewing plane, orthogonally. If they overlap at any point, you sort them by the depth of the inverse orthogonal projection of that overlap point back onto both shapes. You have 2 points, one on each shape. You can order them by the depth using the dot product. And that is, or in this case, I align it along the z-axis, so I don't even need the dot product. And for those of you who are wondering what this is, this diagram took me 16 hours to make in PGF math. 24 frames. And multiple bugs along the way. It took a very long time to make. And this is the same one that took less than 20 minutes by far to produce in Lua, which is why I use Lua now. Simplicial partitioning is achieved through basis navigation and Gauss-Jordan elimination. Gauss-Jordan elimination will take two bases and produce a subspace basis for them if it exists. Otherwise, it'll produce a result that is recognizable to the computer as it does not exist. It might have free variables, or I forget the specifics. And the cool thing is we can navigate that subspace, that new subspace, as a subspace. We get a basis out of this, so we can continue to navigate it the same way we've been navigating everything else. It's basically like steering a ship. It's like driving. Now, this is the big part of the talk. This is the part that I really want to get across to all of you. That's why I put it last. I think that this would be of benefit to the community to hear. There is a gap in parametric tessellation theory that I've noticed, at least. The gap is poor tessellation. Specifically, I am talking about domain restrictions and curvature. I express that in this form of language. Domain restrictions and curvature are the general way to put it, though. Currently, when we tessellate a domain, take it, for instance, for a surface, we will take a Cartesian product of samples along both domain dimensions. And then we will triangulate the resulting grid. By Cartesian product, I mean we take two, usually it's an arithmetic sequence, sometimes it's not, and then we turn them into a giant grid of points based on those two sequences, and then we triangulate those points. This has problems with non-trivial illustrations. I would like to draw illustrations that I cannot draw because of this current technology. I don't have any of those illustrations here today because I only wanted to show good diagrams, but if you're interested, talk to me later. I have a Stack Exchange post that has much worse diagrams that show the issue. When we tessellate a surface domain, it neglects non-trivial, it neglects features relating to domain restrictions and curvature most of the time. And I express that in terms of calculus terminology. So, I'm not going to propose a solution here. I'm not here to predict the future. I'm here to inspire you guys to try and fix this problem yourselves. More creative minds focusing on the same thing. Let's overcome this. So I thought of some things that would likely be involved in a solution. Not necessarily, but this is where my mind went. Instead of a generic grid, we would sample the domain, for instance, for a surface, in this case for a surface, based on its parametric properties, for instance, using Castlake capabilities. That would let us identify very specific regions in its domain where it is doing important things, like inflection points or inflection regions if it's a surface. It could capture asymptotes or domain restrictions, and the idea behind that, the idea behind strategically sampling each of these phenomena is that when we go back later, remember the picture of the green, it looks like Patrick Starr's pants, someone said? When I removed those triangles on top so they wouldn't go all the way through the ceiling, I did that using something called filtering, using a Boolean filter. If we were to tessellate the domain of a parametric object according to its features and not just a random Cartesian product of arithmetic sequences, we could go in and, based on those features, remove simplices that are too close to them or are beyond the boundary. That would be incredibly useful. That would allow us to avoid the asymptote problem, not the software asymptote, the problem with singularities, and the problem of domain restrictions, because not all domain restrictions are asymptotes. But it would let us do that. So the way I was thinking it might happen, I'm not going to say this is how it's going to happen. This is just where my mind went. The sample points in my theory would track the domain boundaries. For instance, they would go around asymptotes, or if the asymptotes spanned a curve, they would traverse around that curve and also along the asymptote. They would also traverse around domain restrictions. And they would not just be adaptive, but they would be deliberately chosen based on the parametric formula. I don't want to reduce this down to just a problem of probability. I want to actually perform rigorous understanding of parametric surfaces using a computer so I can tessellate them better. And it would capture regions of high curvature with more samples, and in order to avoid wasting simplices, which lags our computer by a lot, we would not tessellate so much in areas where it is flat. Currently, when we have a diagram that is, if let's say this floor was a plane, okay, I should probably be on camera, but if we have a parametric surface that is really complicated in one area and not complicated in other areas, why are we wasting triangles in areas that we don't need to waste them in? That slows our computer down. We should not do that.
I think it's lagging.
Yeah.
Okay. How am I doing for time?
I think you're running low.
I think you made the CPU overheat.
Well, I'll talk about this diagram then. This diagram is something very special because we did something here to avoid a tessellation problem. This is a stereographic projection. Ooh. Okay. Thank you.
I was listening.
I'll describe it with the last one because they use the same feature.
It's okay, I can't see it anyway, that's all that matters.
Hopefully this works.
You just wave your hand. Person with first person.
Be accessible, just explain how and
What's the alt text for this guy?
This was included as an. I don't know if you can add alt text to animations. I'm not familiar with that.
Okay, while we are doing this, could you explain the color font, how you create animation?
Absolutely, I would be happy to, after we describe the last slide. So, this slide gets into a bit of a more esoteric issue in sampling theory. I debated whether or not I should add it, but the animation was cool, so I did. Intersecting curved surfaces almost always miss the exact regions of intersection. When we specially tessellate, say, for instance, two spheres, and we intersect them, the result is not actually their intersection, but an approximation of it based on the tessellation. I was actually talking to Charles about this morning, and apparently this is a well-known problem in computer graphics. What I would imagine would be the goal here would be to identify, in order to prevent the need to partition later on, points in the domain where they would map to intersection points. Then we wouldn't need to partition those intersection points because there would already be a partition there. And this diagram is really special because it is a stereographic projection that, as you can see, none of the space is distorted. Normally when you deal with Mobius transformations, some places on the map get really big, and some places get really small. It preserves conformality, but it does not preserve distance. The cool thing about this parameterization is it is a parameterization of the stereographic projection that preserves distances. So circles map to circles under Mobius geometry, and because of that, you can parameterize them in terms of sine and cosine. And there's a theoretical way to prove it. I'm not going to do that here. I do not have a thank you slide. I said my thank yous at the beginning. But as Boris would like to know, and I'd imagine other people maybe who like animations or maybe want to produce their own, how do I do this? The way that I do this is there are multiple ways, but the way I prefer to do it is I use a TIX picture in the standalone document with the TIX document class option. And I usually add a small border around it or no border depending on the illustration. So I would have document class, TIX border equals 1 centimeter, standalone, and then I would use a for each loop on TIX pictures. Because using the TIX class option, each TIX picture will be a unique frame. Now, that will still lead to problems with moving pictures because the frames will be different sizes. You need to use as bounding box. It is very fundamental to that flow. And then once you have the sequence of 24 pages of PDF, in this case, I did something that I don't normally do. I just include animate graphic. I used the package animate to use the command animate graphics to include the PDF. And that is animating the PDF. Normally what I do, though, is I produce GIFs, or GIFs, or however you like to pronounce it. I wouldn't judge anyone for how they pronounce that word, because I don't know how to pronounce it. When I do that, I take the PDF and I use various software, be it ImageMagick, a Python script, or a website, to turn it into a GIF. Thank you.
All right.
Well, I want to keep the duck up.
I know we're running late,
Sorry about that.
and Boris has already had his question answered. If there are no other questions, we can go to the break.
Sorry for taking so long. What? Oh.
That was our side.
Oh, that was yours? Okay.
Yeah, we screwed up.
Oh, you need this. I thought you were giving me a fist bump.
What's gone broken? Because this is not going to work.
No, it's because your computer was lagging.
No, this is messing with the sound.
Wait, let's hit the mute key. Testing, testing. Testing, testing.
Let's make sure it's on.
So sorry. Are we starting or how?
We're going to start.
Okay, yeah, all right.
All right, everyone. We have saved the best for last because I see the announcements for another version of Asymptote come out on C10 on a regular basis. And every once in a while I ask, well, I better go and see what's changed. And I suspect we'll learn more about what has changed. So let's welcome John Bowman from University of Alberta. Past, present, and most importantly, the future.
Thank you. Can you all hear me at the back? I've got a lot of things to hold, and I'm not sure I want to hold a microphone too. So, okay. First, I want to acknowledge my collaborators. Andy Hammerlindell was the one of my undergraduate students back in 2002, and he came to me looking for a summer job, and this is what came out of it: was Asymptote. So here we are. About 25 years later, and another collaborator here is Charles Statz, who's with us here today, and he's contributed a lot of what I have to say in this talk. And also the software that was used to develop this talk was developed with my student Ben Bingham, and also with AI. AI is what pushed it over in this last week to get, for the first time, some of the features I'm going to show you available in a PDF. So, right, so the talk is posted here, and there's a QR code. If you're close enough with the camera, you can take a picture of it. Anyway, so it began in 1978, but I guess the manual came out in 79 for TEC and Metafont. So in the beginning, it all started with Knuth. And then at that point, the companion to TEC, of course, was the font generating program. That was all done with bitmaps. And so now, we are using much nicer looking fonts, and that's due to the work of Hobby. He realized that the problem was really figuring out how to pick control points for drawing nice, smooth looking curves through some points that you specify that you want to use for making your fonts. And so he developed this concept of mock curvature. It was efficient. It could be solved with just a tri-diagonal solver. And that was very important back then. So they could very quickly calculate these control points, and then they can be rendered by subdivision very efficiently. So, so that was for producing fonts at that point. But then in 1989, Hobby realized that he could, if you can make nice fonts, then well, you could also make nice curves and do graphics. And so that was what began Metapost, and Metapost is what inspired Asymptote. Because when Andy Hammerlindell came to me and looked for a summer job, I said, well, there is one thing I see. There's this program Metapost. I've been trying to, it seems to be the best thing out there for this Venn diagram I wanted to produce. And I wanted vector graphics. That was one requirement. But I also wanted IEEE numerics. And of course, this software was all written before the IEEE standard back in 1978. It was before the IEEE standard was a thing. And so I wanted to modernize Metapost, and I looked at the code and I thought it doesn't look like any way we could upgrade the numerics. It's too based on TEC. So my decision was to go away from TEC, use TEC, but redo the whole numerics. And Andy, I gave it to Andy and asked him, well, take a look. Maybe your opinion is different. But he came back a few days later and he said, yeah, you're right. We're going to have to start from scratch. And so 6 months later, he read a book on compilers and wrote his own compiler for a virtual machine that could produce a little straight line. And I thought, well, that's pretty cool, but how about, let's make a sine curve or something. Well, he said, well, we can't do it yet because it doesn't know about sine, but let me type on your computer for a minute, and you hack, and he hooked it up to the floating point sine instruction, and lo and behold, we had a tiny little sine wave, and that was the beginning of Asymptote. And then I was at a conference, and I learned how to overlay with TEC because this was just producing PostScript at this point. There was no tech involved at all. But, and unlike the way it was done previously in MetaPost, I diverged from the method that was used there. I wanted to really use tech itself, and I didn't want to get into redo what Knuth did, because he did an excellent job with typesetting. And so let's not reinvent the wheel, let's build on that. And so Asymptote at that point was just a way of producing a tech file for you that would bring in with include graphics, or whatever we used back then, EPSF or something. It would bring in your graphics and interlace it with tech. And, but that was all 2D. Then in 2005, so this was our first public release. We started in 2002, but it wasn't released until then. And it's the same time that TIX was released, and neither of us knew about each other's projects. Otherwise maybe there could have been some collaboration there, but we did really choose very different approaches to the problem. The fact that we didn't really build into the tech ecosystem, we just used it. Okay, that gave us freedom to do more things, particularly when it came to doing 3D. So the trouble with 3D is, first of all, tech is a 2D program, and at the last TUG meeting I was at back in 2010, I met John Hobby and showed him what I was able to do and the difficulties I had extending his algorithm, the same mock curvature algorithm, but a generalization of it into 3D. And there are some issues, some parity issues that you have to deal with. And that's all in this publication here. So that then gave us the ability to lift tech into 3D. And we wrote an OpenGL renderer, and even figured out, I had a student, Urs Shard, who helped me figure out how to embed this in PDF using this legacy PRC format. And if I was giving this talk back then, that's what I would be using to show you 3D graphics. Unfortunately, PRC, I'm going to discuss, is not a viable option anymore, and we need something else. And that's partly what this talk is about. So another thing that happened shortly after that was because the labels in tech, even though I've lifted them to 3D, they're still planar. And if you rotate your graph, you'll be viewing those labels edgewise, and it's not going to look very nice. So one of the important advances was allowing those billboard labels to rotate so that they always face the camera, no matter how, and you'll see examples of that, no matter what viewpoint you're looking at. And there were various 3D PDF enhancements which were done with a colleague from Russia, Mikhail Vidivosov, and that's mentioned in this article, in another Tugboat article. And another missing feature at that point that we added in with Bezier triangle patches. Those are useful. Bezier triangle is a natural generalization of a triangle to 3D. Then a student who goes by the name of Jamie, Rasame Masmuang, and he independently contributed a better rendering model than the Phong blend model, which I was using. I was just using the simplest model. He uses this PBR-based approach, a more physics-based approach, and also image-based lighting. I'll show you an example of that. And he helped me develop this WebGL output format using a JavaScript library that we wrote together. And Jamie also helped me develop a replacement to the PRC format that I mentioned. It's a new format. I call it Vector 3D, V3D. And it's compressed. It's even better compression than the PRC format. That was one of the big deals about PRC. The trouble with PRC is one of the way they implemented their own compression algorithm. There's good compression algorithms out there. I didn't have to reinvent the wheel. So we used gzip. And also another thing that's been missing from 3D graphics up to this point, so 5 years ago I finally implemented exact pixel perfect order independent transparency in 3D. And that's really hard to achieve and to do it efficiently. And the problem with transparency is what makes it so hard mathematically is that the blending operation that we use is non-associative. And it means you have to sort the fragments that get mapped to a pixel, you have to sort them usually from back to front, and you can't interchange that order. So although with opaque objects, the painter's algorithm allows you to graph in OpenGL in an order-independent manner, that all breaks down when you have transparency. And to do this correctly, you need to be able to, you need advanced hardware features of the GPUs. We all have those features, but the software is kind of lagging, and that's one of the problems, as we'll see. There have been a lot of language improvements thanks to the work of Charles Statz. He introduced the templated imports, the using and auto unravel keywords. I'll talk about those briefly. There's a front end, XASI, a graphical front end that's been upgraded recently to use Qt6. And this collections library, also introduced by Charles Statz. He put a lot of work into this. It's a massive project. There's an iteration facility with an iterator operator. You can now index, have user-defined index operators on your structures. You've got hashing. And the most recent thing we've done is a big thing that I'm sure that Carl is looking forward to helping me with next year in the Tech Live release. We have transitioned over to Vulkan, okay, and all the wonderful Vulkan libraries. We'll have to be talking about that next year, yeah. I deliberately saved this Vulkan transition until after the 26th release. Yeah, I knew you would be happy. And then what I'm using for this talk is this V3D Aware PDF plugin, which we just we just got to get working this week. Okay, so it's very brand new. Okay, so for this, it's used for this talk. Okay, so this is the one of the important contributions. Sometimes you want to import a module in Asymptote. You want to write a generic module for different cases, different types, and you don't have to have different copies of that module and have to maintain different copies, one for each type. You know, maybe one for reals, and one for ints, and one for complex numbers, or whatever. Or maybe it's a sorting algorithm or something. Whatever, we wanted a way, we had some kludgy ways of doing this before. Now we have an elegant, robust way that involves in your module, you tell it that there's a generic type T and a generic type S and another one called number. And you can now, when you actually go to import this module in the calling module, in the parent file, you can access it using telling it what T is and what S is in this particular instance. And Charles recommends you can call this module anything you want. You have to say as something. But he recommends, as a good practice, that you actually name the module with some indication what these different types are, because you may have more than one access of a module with different types. Okay, so this enables generic type-safe library code written entirely in Asymptote. And we also, just like C++, we added a using keyword instead of a type def. And it's just more convenient. It's not so backwards like type def is. And to many of us, we always felt it was a little, the type def is a little bit awkward, and it actually is necessary in this language when you're referring to function types. In certain contexts, you need to use this type def. It's actually required. It's not just a convenience. This makes it a little easier. And there's also a new auto unravel feature, which is quite convenient. What that does is if you have say a structure with a member function, an operator plus, that operates on two of those structures, rational, for example. So this is an example of a structure that implements rational numbers, and you want to add two rational numbers. If we didn't have this auto unravel keyword, this would have to be declared outside of the structure. And this way you can keep everything nice and self-contained, and you can still access it outside. The auto unravel basically unravels this out of the structure so that the plus operator is now accessible wherever rational is used. And so that's really nice. And then Charles went on to develop all kinds of containers to help us out with some functionality that we were missing, or it was very awkward to do these things before. And so this is a very, very thorough package these set up for doing hash maps and hash sets, sorted sets, queues, and also native hashing of int strings, reals, and int arrays. They can be used as map keys. For example, so from his collections library, you can access, it sort of looks a bit like Python, right? I mean, the from part, right? And you're accessing this module is this key value hash map. You can access it as this particular name. Again, I'm following Charles's recommendation. And then that's now a type that you can use. And so we're going to, the instance of that type we're going to use is little h. And then we can now, it's like a dictionary. We can assign to various strings, we can assign some integers, 4 and 2, and then we can write them out and we get 42. Okay, so another example, you might be doing a frequency analysis on pets, see which are the most common pets. So you got a list of pets. And I didn't have room here for a long name, so I just called my hash map h. So I create an instance of that hash map called counts, and I can iterate on it, and so I simply increment for each. I go through this list for every pet. I do a frequency analysis, and so I know how many pets I have of each type, and then we can graph it out. So this is just the code for producing this graph, and you see that the cats win. There's 3 cats and 2 dogs and 1 bird. Okay, so another thing. There are some iterator utilities, zip and enumerate. Here's an example of how you use zip. It just allows you to, like a zipper, go back, join A with 1 and B with 2 and C with 3. And so we write them out here. So basically, it's another way of doing key value pairs. But you can combine any 2 arrays this way. You can zip them together of the same type or different types. So also these bracket operators, if you suppose you define your own structure, you might want to define what the bracket operator does on that structure. So that's quite convenient. We couldn't do things like this before. And so these are all enhancements to the language. Okay. Now I want to talk about what's been done on the rendering side. So all the 3D work is based on Bezier surfaces and curves as well. But the most difficult part are the surfaces, because you have to deal with occlusion and lighting and subdivision cracks, rendering, all kinds of issues. The fundamental atoms of 3D graphics for Asymptote are Bezier triangles and patches. So Bezier triangles are the natural generalization of Bezier curves to surfaces, just as triangles are the natural generalization of straight lines to planar surfaces. So the Bezier triangles are curved, and they also have a one interior control point that you can use to lift the interior up or down a little bit. So they have a total of 10 control points. A Bezier triangle can be conveniently expressed in barycentric coordinates. By the way, I'm talking about the cubic case here. Okay, this is the usual case that's used in computer graphics. We're using cubic splines. Okay, so Bezier patches, they're the direct product of 2 such Bezier splines, okay, 2 Bezier curves. It's the direct product. And they're like the generalization of quadrilaterals to non-planar surfaces. Okay, so you've got something like curved triangles and curved quadrilaterals. We call those Bezier triangles and Bezier patches. Here's a Bezier triangle, and this is now done with the new plugin that allows us to have finally, back in 2010, even 2008, I could do this when I was teaching, and I could, when I had surfaces of revolution in my calculus classes, my students were on their laptops, and they all had Adobe Reader, and they could view this with Adobe Reader. But unfortunately, Adobe Reader a few years later was no longer supported on the machines, on the new machines the students had. They had tablets and phones, and also Adobe Reader stopped supporting Linux and other OSs. So they still, I guess, support Windows and Mac OS, but very few people seem to use them. More people are using things like Chrome browser and other browsers out there. So it's great after all these years to finally have this functionality that in a PDF presentation, that I can do graphics without having to leave the presentation to another piece of software. So, so let me just mention a few of the problems of this PRC. It stood for Product Représentation Compact. It was a French product. They also had the acronym PRÉCISE because it was meant to be very compact and precise. And, but the problem is it was only, no one wrote a reader for it. We wrote a writer, and we could have turned all the write statements and read statements and made a reader for it. But there's other problems too, okay? Also, another big problem is Adobe Acrobat, even though it sort of worked, it wasn't adaptive. It was not vector graphics. The initial mesh you got on loading was the mesh you got when you zoomed. It never got better. So that's not vector graphics. So, and it had no 3D transparency. It didn't have vertex-dependent colors, which made everything look really, really pixelated when you did scientific graphs. And no Bezier triangle support. So I used AI to help me prepare this talk, and the AI wanted an example of PRC. It says, I can't put an example in. That's the whole problem. That's the whole point of the talk. I can't do it anymore. So we developed a new format called V3D and Vector 3D. It replaces this legacy format. It's a portable compressed vector graphics format for 3D scenes. It's embeddable in PDFs. And it's importable back into Asymptote. And it has 3D transparency. It has all the things I want, vertex-dependent colors. I basically put everything in that I want. And we're on version 2 right now. It's an integer. We're going to just keep incrementing the integer as people submit new, request new features. We can always extend it. It has also some primitives built in, which are common primitives in graphics that you can use in drawing. For example, tubes are very useful if you want to draw a thick line. In OpenGL, you can only be sure of a 1 pixel wide line be supported. That's all that the standard guarantees. So if you want to draw anything more, you have to draw a surface around that 1 pixel line. Also, we support triangular groups, which are useful for tessellation, and also curves in 3D and even pixels. As I said, there's a bunch of viewers for V3D. We're working on getting more available, but one of them is Asymptote itself. It can read its own files, which is always nice. And there is a library for programmatic access to it. But the real tool that we're going to encourage people to use for the time being right now is Ocular. We've developed a plugin for it, and that's what I'm using today. And so I will announce it soon once it's completely stable. If it survives this talk, that's already a good sign. It hasn't crashed yet. There's also, we've had for some time now, for a year or two, we've had this online JavaScript PDF viewer that can read V3D. And so that's another possibility. You've got to read that through a browser. So here is an example of, I think I showed this in 2010, this whoops, I forgot, I can't zoom that way. Okay, when you zoom, you're scrolling the document. When you use the mouse wheel, it scrolls the document. So I don't want to have contention between two. Normally the mouse wheel would zoom like that. But anyway, you can see that I've really lifted tech into 3D. And Donald Knuth really was impressed with this when I showed it to him, that to see his work now in 3D. And it was a lot of fun doing this. And this is just a little, there used to be this package, PS Tricks. Anybody ever use it? Anyway, you don't need it anymore. There's better ways. Okay? Okay, and here you see the billboard labels. Okay, and maybe I can zoom in a little bit so you can just see them as they rotate. As we rotate around, they don't disappear. They're always facing the camera. And the other thing that's nice about this picture is that you don't see pixelization. Oh, sorry, I forget. I can't zoom like that. You don't see pixelization. If I showed this with Adobe Acrobat, you would see all these. You basically see the mesh, and that's not good. So underlying this, there is a mesh that I used to generate that. That's a 3D gamma function on the complex plane, by the way, and so along this red, you're mapping a function from R2 to R2. It's a 3D graph. The fourth dimension is I use the color wheel. So red means real, And RGB goes around that gives you the phase of the complex number. And I'm plotting the magnitude here versus the real and imaginary parts. And the factorial is just along here. So you can see how this is very good, useful for teaching to be able to do this. So that's the factorial right up there, the usual factorial along the real axes. Okay, so this is just showing you that we've implemented transparency. Whoops, and we just got this working this week, and AI did this for us. It was like a 3-hour session with my student, and this is all local AI. I'll tell you about that more. Here's another case where transparency is useful. There's a graph here, and you see there's some data that's above the plane and some's below. You still want to see the data, but you might want to be able to understand what's in front and what's behind the plane, or above and below. Here's a nice calculus problem. So there's an exercise afterwards. You can calculate the surface area of the sphere that's inside the cylinder, and that's a fun exercise. And again, we have transparency in that example. This is the Riemann surface, the Riemann sphere, and which shows you the projection of the sphere onto the plane. It's a very nice way of understanding the complex world that we live in. And Charles contributed this wonderful package for drawing smooth surfaces. It's just beautiful. Yeah. So it's interesting how he did that. And he used Bezier triangles. Once we had them available, he updated his tessellation of this so that it makes use of both quads and triangles, Bezier patches and triangles. Okay, so like I said, we've migrated from OpenGL to Vulkan, and but we didn't force people to you don't have to use Vulkan. If you don't have the library available, there's a fallback to OpenGL. Okay, so we dynamically load the OpenGL library. But eventually, I think, especially for Mac OS users, they definitely want to install the Vulkan library, because otherwise, they don't have transparency. And that's because Mac OS basically deprecated OpenGL. Their OpenGL goes back to 2013, and they just froze it there. And so all the new features that we need, the new feature we need is from 2013, and it's not in there, and to have transparency. So that is now available through the Vulkan using Molten on top of the Apple Metal platform. This gives consistent rendering across all operating systems, better GPU utilization. And finally, I mentioned that we also produce WebGL figures. So this is a way of embedding 3D figures directly in HTML. And it's using a JavaScript library that you either download from the network, or you can embed it in a standalone file if you want offline access. And in this way, this brought Asymptote, not the program, but the output, to tablets and phones, but with a little bit of a drawback, is there's no order-independent transparency. So we have to solve this problem. And in order to do that, we're going to have to migrate to WebGPU. But here's a nice example that I just did recently. I added the ability to do animations by specifying, before you draw a surface, you can enclose it in a transform, begin transform and end transform. And this is a function that's going to map your coordinates and time to another function, to a new coordinate. So this is giving some affine transformation here that we're doing. And here we're going to, that's the geometry transformation. There's also a color transformation. So you can change depending on the position and the color and the time, you can do something fancy, and it leads to something like this. So let's click on that and see what happens. Oh my. I mean, it's just craziness, right? I just had lots of fun. Deconstructing the Utah teapot. Okay. All right, so that's that example. And here's another example. It was contributed by an Asymptote user who also contributed to the animation. He certainly, by asking good questions and even submitting patches, he helped make this possible. So, this is a robot. So he's I guess he's a robotics engineer. And I don't know his real name, but his handle is Asm Warrior. And you got this robot. You can move it up, and so you can even let's see. You can do that, and what do I want to do here? Then okay, and then move it up, and we can try to reach out and grab you or something. Okay, so all right. So that's fun for educational purpose for sure. And as I mentioned, we need to improve on WebGL by upgrading to WebGPU. So that's a project in the next months. I'll be working on that, and that will give us access to the hardware features like shader storage buffers and that are on GPUs, the SSBOs that we need, and this will also improve the performance too on modern GPUs, and it'll give us order-independent transparency. That's the main thing. And another thing that that my former student Jamie did was this image-based lighting, and I'll just show you an example here. Isn't that cool? And it's all interactive too. You can move around here. There we are. Yeah, isn't that cool? I look at that figure, and to me it looks like Edmonton in the winter. Okay, so you got the snow and you got the evergreen trees. I think it was actually from Russia, but it's pretty much the same thing. It's not the end of the world, Edmonton, but you can see it from there. Yeah. Okay, so yeah, as I mentioned, we also did an upgrade of XASI to Qt6. That was necessary for compatibility with different distributions, and XASI allows interactive editing of asymptote figures. You can modify existing objects, you can draw new objects, and you can save those objects either as normal asymptote files or in another format that allows you to go and edit the objects that you created. So it kind of combines the best features of script-driven and graphical-based methods of figure creation. So it kind of marries these two approaches. And so just in summary of what I've told you today, there's some new language features, templated imports, the most important one, and the collections library, these new the bracket indexing and things like that. Sometimes these are syntactic sugar for things we could have done before, but they're nicer looking. And then we've got the Vulkan port, the WebGL, image-based lighting, triangle patches, lots of things, a huge long list. I was surprised when I saw just how much that we've done in the last, since I last spoke at TUG back in 2010. And yeah, and then this plugin we've used. And so in the future, well, I don't have a long list here of things to do, but I'm sure that I can't predict the future, but I'm sure there will be many things. But I've already mentioned the WebGPU migration. That's really important. And we would like to add animations, just like we have that animation. That was only on HTML. I'd like to have it in V3D, so I'm going to have to modify my V3D format to support animations, maybe doing something similar. And here's the last one I've learned at this conference, the need to support accessibility. Now, how to do that in graphics is a real challenge, but I'm certainly interested in hearing ideas about it. There was a project to try to add Braille support for Asymptote, and I should inquire what the status of that is. Okay. But thanks so much for listening, and then I hope that I'll have a chance to talk to you all at the banquet. Yeah.
Thank you.
Oh, here, by the way, is this is our logo, and also on this page, this is the controller that I wrote for doing local AI. I run this talk was partially written by AI on a 5090 NVIDIA 5090 card, and using the Qwen 3.6 model, which is really an awesome model, as Matthew was saying the other day. So you can get this controller from there. It does agentic AI operations in a sandbox on your local computer, and it works much better than using ChatGPT or Gemini or something. So you may want to try it out. Yeah.
Okay, now surely there's a question. I'm looking at you, Boris.
Boris always has a question. You can help us out, right?
I have only
Only comment, right?
Yeah, I have a comment
Of course.
from chat, and it's very short. It just says bravo.
Oh, no. Oh, you're welcome. I think we have a question here.
So for the generic functions you added, there's no type inference there. You have to manually name the function for each type.
So the generic functions, are you talking about the using keyword we're
Yeah,
talking about?
yeah, because you just specify this different name for every type, so it can't just use type inference to figure out what you mean.
That's right. Yeah,
Okay, yeah.
yeah. Oh, okay, well, maybe Charles can answer that. Yeah.
The functions can be automatically inferred. The types, based on what parameters you cast. Okay, yeah.
Yes, that's true.
The function you can have one name for the function, and there's no worry about name collision. But the type you have to. That's magnetic. You have to have a different type. Well, if you want to avoid name collisions, then you want to rename the type every time you import it with a different set of parameters. In a lot of languages like C++, they use angle brackets for that. I didn't want to try to add the new angle bracket syntax, so we use underscores incorporated into the type name. And if you really don't like underscores, then you can make up your own convention and incorporate that into the type name.
Okay, thank you.
Yeah.
I'm sure I don't need the microphone. I can project my
Well, for the our online people, we need it. Yeah.
Hello, this is Jasper. My question is related to a module of Asymptote that I am aware of called Smooth Contour 3, which lets you plot implicit surfaces.
Yes.
I've seen that used to perform things that are very similar, in my view, to partitioning. I have a picture on my laptop here. I'll probably show it to you afterwards.
Sounds good.
I was wondering if that same procedure with the implicit surfaces, such as the genus 3 surface,
Yes.
could be used to handle more advanced partitioning features as they do in, for example, when you have a plane partitioned by a cube.
Yeah, well, one thing, if you have a plane partitioned by a cube, I think the best way to do that is at the pixel level. And we actually have another thing I forgot to mention, which should be on the future slide, is an unfill operation, which is a project that's partially completed. And using AI, I can probably, again, push this one to across the finish line. So in 2D, PostScript does unfill by whenever you draw a pixel, it checks to see whether it's inside a particular Bezier curve or not. We can do the same kind of thing in 3D. We have something, a prototype implemented, but it still has a lot of problems. But that would be how I would try to do that particular problem. But there are more general issues with intersecting surfaces. And so maybe Charles can speak to this, because he wrote this wonderful package. And I know he has ideas on how to do cropping in 3D.
I'm quoting Charles, actually. Yeah. I'm quoting his Stack Exchange answer to my post
from
of course, a while ago, probably from 2025 January.
Yeah. So I don't know if Charles wants to comment more. Yeah, I think he would like to. Yeah. Charles didn't want to give a talk, so I told him, I'll talk about all your work, and then when I say something wrong, you can correct me. And see, it's working. Yeah.
Okay, so I do. It's been on my to-do list for a long time to see if I can use these same sorts of techniques to, as an alternative to John's approach with the unfill, to see if we can truncate surfaces that aren't defined implicitly. I sort of put that on the back burner because I was really frustrated about trying to do this sort of thing without a collections library. So that's one of the reasons I went to the effort of creating a collections library, is to make it easier to work on those sorts of things.
Well, we have something to look forward to, so that should also be on my future slide. Yeah. Okay. Yeah.
Did you also, when you used OpenGL, did you also use custom shader programs?
Yes. Yes, and I should say that was another thing that should have been on that list that my former student Jamie did. They're still working with me part-time. but they're the ones who got me to move away from begin GL and end GL or whatever, the old way of doing OpenGL to using the shaders. And so because we have the shaders, now we can do wonderful things like the transparency. Everything that's done at the pixel level, we can do at the unfill operation. It opens up whole new approaches. So we've had that for a few years now, maybe back 4 or 5 years, yeah, something like that. Yeah.
And was it like a rasterizer implementation or deferred rendering?
Deferred rendering. Well, that means something else, I think, in Asymptote, what we call deferred rendering. We are rasterizing, but we're doing adaptively. So first, what we do is we turn Bezier patches into triangles. We wrote our own. When I say we wrote our in-house renderer, it's just for turning the patches into triangles. Once we have the triangles, we give that to OpenGL and let that handle, because it handles triangles well, using the OpenGL shaders. And those same shaders, with some modifications, worked in Vulkan too, and they're also being used in this talk here. Those same shaders are copied over to the plugin as well. Yes.
Okay, thank you.
Yeah.
All right. We'll thank our speaker one last time. And now, Eric will continue the program.
Okay. I'll give you back.
Well, actually, I'm going to close it in a bit, but.
Okay, there's all your cables. Thank you so much for sending that
Okay,
up.
so before I close the conference, you all are to remain seated. However, we're going to close the YouTube feed in a moment. So before closing, I would like to thank all talkers of today. Give them a great applause. And yet another time for the conference committee, of course. Also a great applause. Yeah. So I hereby close the conference and will give the mic to Carl Berry.